since we're a little discombobulated with the schedules this week. Okay, remember these two assignments are due on Monday. So if you've already got part of it done, awesome. If not, you have tomorrow and Saturday and Sunday to get it done. I don't see you tomorrow, unfortunately. So you get a break, I guess, from me. Okay, today we are going to spend a moment talking about inverses. Does anybody have any idea about inverse functions? Can you remember anything about inverse functions, Bailey? Okay, Bailey is telling me how to find the inverse. So this is the notation for inverse. This is a little F inverse. When we read that, we read it F inverse. Okay, it means the inverse of F. That's not an exponent, that's the notation for the inverse of F. Okay? Now, remember, oh, here's a problem. Let's just do this problem. Remember, f of x is the same as y. So Bailey says, I know I'm supposed to switch the x and the y. So she's going to take this equation, which was the given, and she's going to rewrite it like this. And then what, Bailey? Do you remember?
Solve for y.
Solve for y. So then we just solve for y. So your inverse is x minus 1 over 3. Now, I really want you to think about this for a second. If your function f, and you get a number, like 4, somebody sticks 4 in, what happens to you? First, you get times by 3, and then we add 1, okay? So we times by 3 and we add 1. Now look at what the inverse does. The inverse takes the number and does what to it? Subtracts 1 and divides by 3. Do you see how it undoes what the original one did? This is a machine. He times this by 3 and adds 1. What does the inverse do? Puts you in reverse. Subtracts the 1 and divides by 3. So look what happens to the order of pairs. In the original, if I stick a 4 in, I get a 13 out, right? We'll come over here, put a 13 in, and what comes out? You undo each other. When Bailey said you switch the x's and the y's, that is exactly what happens. Inverses undo each other. Okay? Let's try a little harder one. What if we had to find the inverse of this function? We want to find the inverse of that function. Now, we're going to use Bailey's steps exactly. So, this is the same as y equals, right? Remember, g of x is the same as y. So now I'll switch my variables. But this is a little tougher because, Dan, what did you say I'm supposed to do now?
Solve for y.
Solve for y. So somehow, I got to get y by itself. By the way, anybody know what year Mr. Berner graduated? 19 what? Close. He would like that. He's actually before that. 84? So anybody that said anything between 81 and 87? 88 was an awesome year. There were some great kids in the class of 88. Mr. McGinley was in the class of 88. But 84 was kind of a hell of a Okay. Now, any ideas how we might solve that? Jamie?
it by the bottom.
So clear the fraction, in other words. So we're gonna clear the fraction, multiply both sides by the denominator. Now remember what your objective is. You're trying to get y by itself. What some kids will try to do is, don't write this down because it's not right, but some kids will do this. They'll add 1 and then divide by 2. Now, do they have y by itself? Well, they got a y over here by itself, but what? There's still a y on this side, so that's not legal. We do not want to do that. So what do you suggest if that's not the option that we're going to choose? Dan?
Can you divide by x then?
Oh, Dan? Divide by x? Okay, let's talk about that. We never, ever divide by a variable unless we are absolutely sure that it cannot be what? 0. Yeah, so that's a no-no. We're not going to do that. Other than?
Subtract 2y
Well, I think part of that, I like part of that idea. Emma?
Distribute x.
Well, we can start with that. Now remember, we're trying to get y by itself, right?
So the y out.
So then, instead of moving everything over, let's move this guy over here and this guy over here. So that every term with a y is together, and every term without a y is together. Do you follow that? We're just rearranging the equation so that all the y's are on one side and everything else is on the other side. Now, what might I do with those y's? Take it out. How many y's do I now have in my problem, kids? 1. Can I get it by itself? Yes. How can I get it by itself? Divide. So y equals negative 5x minus 1 over 3x minus 2. Now, Dan is sitting there saying to me, well, Mrs. Ford, you just told me we're not going to divide by variables unless we're absolutely sure it can't be 0, right? But I just divided by a variable. I mean, it was part of an expression, but I basically divided by a variable. Here's what I need you to get. This is our inverse. This is our original. Now, do you remember a moment ago we looked at the ordered pairs? And we said the ordered pairs between these two will flip-flop, right? That's what inverses do. So I want you to look at this problem, the original problem, and I want you to tell me about its domain and range. You should be able to do that. What is the domain of this original problem? X can't be negative 5/3, right? That is absolutely implied. If it's not stated, it's certainly implied. You can't have x be negative 5/3 because that would put a 0 in the denominator. Tell me about the range of this guy. Think horizontal asymptote. Does it have a horizontal asymptote? Where is it? So your range is y cannot be 2/3. Because when you graph this thing, there would be an asymptote at 2/3, right? And you'd have picture up here and picture down here, but it wouldn't touch that asymptote. Correct? Now, I want you to think about this for a second. If these were the restrictions of the original, what will have to be the restrictions of the new one? Remember, the ordered pairs switch. So if you tell me y can't be 2/3 in the original, what do I absolutely know? X cannot be 2/3 in the inverse. Does that pan out? And if you tell me x can't be negative 5/3 in the original, then y can't be negative 5/3 in the inverse. And that pans out too, doesn't it? That would be your horizontal asymptote. Okay, ordered pairs, flip-flop. Now, one more quick comment about inverses and then we'll be done. Let's look at, let's say we have 1, 2, and 0, 3, and maybe 1, negative 2. No, I better not do that, I made a function. 2, negative 2. Now let's plot the inverse of those points. Okay, so what would the inverse of this be? 2, 1, and 3, 0, or 2, 1. 2, 1, 3, 0, and negative 2, 2. Now it's kind of hard to tell on my picture, but I want you to envision the identity line running down through the middle of that. Remember your identity? Tell me about the relationship. Okay, this was 1 point, this was its inverse point. That was 1 point, this was its inverse point. That was 1, and this was its inverse. Tell me about the relationship between the purple points and the black points. What?
Are they odd?
Oh, is it odd?
They're symmetrical.
Well, to be odd, it would need to be symmetric about the origin. These 2 points, Victoria, aren't flipping across the origin. What are they flipping across? The identity line. They have symmetry about the line y equals x. And that makes sense to us because it goes back to what Bailey said in the very beginning. How do you find inverses? You switch y and x. So what happens when you switch y and x? You're symmetric about the identity line. Yep, so inverses are symmetric about the identity. Okay, we got your homework. It's like Friday, so I'm going to give